All right, so today is day 39. I review some like code I did like quite some time ago. It has like many different things. Today I don't have too much time to review everything that I did, but in essence, it's I don't know like PyTorch, like some PyTorch introduction, like all the components, also neural networks from scratch. The most interesting thing I would say from this one specifically it's the how to do backpropagation from scratch, because we know that 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 PyTorch behind the curtains computes the gradients. But how does it do it? I mean, it constructs like a graph and then backpropagates each node, traverses like the node by reverse topological order, right? And the way it does it, it's depending on the operator it applies each layer before, it performs the specific operation, right? So if there is, I don't know, like softmax, it's a cross entropy, we can the gradient to respect to x, it's gonna be this one. It's the probability minus the one hot encoding, and then we can actually compute these all the partial derivatives and accumulate them with the chain rule, and then move the weights in that direction. That's essentially what will happen. And for example, in W2, the derivative, if this is the formula, the derivative of W respect to of the loss to respect to W2, it's gonna be W of k minus 1, which is x1, matmul, matrix multiplication with the derivative of the activation layer, which in this case there is no activation layer, so it's 1, and then it's times the one before, the gradient, the accumulated before times the transpose. All right. And we do this like for all the other one. In this case, we take the derivative of the activation, which is the relu, and the derivative, which is this one, right? Because we know that the relu is constant, is proportional, is linear in one segment, and we know that the derivative in that segment is 1, and it's 0 in the other segment, and we know that the derivative of 0 is going to be 0. So, and then also the length, which is just using like some convolution of layers, batch normalization, what else, max pooling. Then if we want to calculate the parameters, right, and also how convolution works, or 3D, even 3D convolution, what else? Okay, that's it. Then also CBAU, the continuous bag of words. What else? So basically, how do you actually perform embeddings of some word, which is basically you assume they are like parameters that you learn, and then in order to do that, you create like an embedding layer and a linear layer, and then make the forward. What else? This is important thing. It's gonna be vocab size, embedding size. So you can think of the embedding as a matrix, that it's like a lookup. So you take for a given token, you're gonna have a vector that represents the meaning of the word in the high dimensional space, right? And n-grams iterator, it's like the context. Then we have the prediction, which is the center word. With this we can create like a data set, load it in the class data loader. You can use an optimizer. This would be the loss. What else? Also, to predict a particular example, if you use a fake mini batch, we are adding a dimension, and then in the prediction where we are squeezing, getting the top k. We are testing the embeddings, Right. What else? This one. This one is recurrent with recurrent neural networks. Actually, I believe. Let me check. Setting the padding. What's the model? Okay, it doesn't matter. But there are like so many different models. It could get pretty complex implementing everything by scratch. In this case, this notebook is implementing also like the attention from scratch. So you have to create the positional encoding and also the actual transformer, which uses the encoder and the decoder. And it's very similar, both of them. What is this one? Also about the attention. But this is with a deterministic dataset. So it's like a machine code, something like this. And this is a vision transformer. Alright. That was basically it.